view quality subjectively and in relation to differing criteria based on their individual roles in the production marketing value chain. In addition, the meaning of quality continues to evolve as the quality profession grows and matures. Neither consultants nor business professionals agree on a universal definition. Thus, it is important to understand the various perspectives from which quality is viewed in order to fully appreciate the role it plays in the many parts of a business organization. One common notion of quality often used by consumers is that it is synonymous with superiority or excellence. In 1931, Schuhart first defined quality as the goodness of a product. This view is referred to as the transcendent definition of quality. In this sense, quality is both absolute and universally recognizable, a mark of uncompromising standards and high achievement. As such, it cannot be defined precisely. You just know it when you see it. It is often loosely related to a comparison of features and characteristics of products and promulgated by marketing efforts aimed at developing quality as an image variable in the minds of consumers. Excellence is abstract and subjective, however, and standards or excellence may vary considerably among individuals. Hence, the transcendent definition is of little practical value to managers. It does not provide a means by which quality can be measured or assessed as a basis for decision making. Another definition of quality is that it is a function of a specific measurable variable and that differences in quality reflect differences in quantity of some product attribute, such as in the number of stitches per inch on a shirt or in the number of cylinders in an engine. This assessment implies that higher increasing amounts of product characteristics are equivalent to higher quality. As a result, quality is often mistakenly assumed to be related to price. The higher the price, the higher the quality. A product, either a manufactured good or a service, need not be expensive to be considered a quality product by consumers. Also, as with the notion of excellence, the assessment of product attributes may vary considerably among individuals. A third definition of quality is based on the presumption that quality is determined by what a customer wants. Individuals have different wants and needs and hence different quality standards. This leads to a user-based definition. Quality is defined as fitness for intended use, or how well the product performs its intended function. Both a Cadillac and a smart car are fit for use, for example, but they serve different needs and different groups of customers. If you want a highway touring vehicle with luxury amenities, then a Cadillac may better satisfy your needs. If you want a vehicle for commuting in a congested urban environment, a smart car might be preferable. A fourth approach to defining quality is based on value, that is the relationship of usefulness or satisfaction to price. From this perspective, a quality product is one that is as useful as competing products and is sold at a lower price, or one that offers greater usefulness or satisfaction at a comparable price. Thus, one might purchase a generic product rather than a brand name one, if it performs as well as the brand name product at a lower price. Competition demands that businesses seek to satisfy consumers' needs at lower prices. The value approach to quality incorporates a firm's goal of balancing product characteristics, the customer side of quality, with internal efficiencies, the operation side. A fifth view of quality is manufacturing based and defines quality as the desirable outcome of engineering and manufacturing practice or conformance to specifications. Specifications are targets and tolerances determined by designers of products and services. Targets are the ideal values for which production is to strive. Tolerances are specified because designers recognize that it is impossible to meet targets all of the time in manufacturing. Conformance to specifications is a key definition of quality because it provides a means of measuring quality. Specifications are meaningless, however, if they do not reflect attributes that are deemed important to the consumer. Although product quality should be important to all individuals throughout the value chain, how quality is viewed mainly depends on one's position in the value chain. That is, whether one is the designer, manufacturer or service provider, distributor or customer. To understand this concept more clearly from a manufacturing perspective, examine the figure. The customer is the driving force for the production of goods and services, and customers generally view quality from either the transcendent or the product-based perspective. The goods and services produced should meet customers' needs. Indeed, business organizations' existence depend upon meeting customer needs. It is the role of the marketing function to determine these needs. A product that meets customer needs can rightly be described as a quality product. Hence, the user-based definition of quality is meaningful to people who work in marketing. The manufacturer must translate customer requirements into detailed product and process specifications. Making this translation is the role of research and development, product design, and engineering. Product specifications might address such attributes as size, form, finish, taste, dimensions, tolerances, materials, operational characteristics, and safety features. Process specifications indicate the types of equipment, tools, and facilities to be used in production. Product designers must balance performance and cost to meet marketing objectives. Thus, the value-based definition of quality is most useful at this stage. A great deal of variation can occur during manufacturing operations. Machine settings can fall out of adjustment, operators and assemblers can make mistakes, materials can be defective. Even in the most closely controlled process, specific variations in product output are inevitable and unpredictable. The manufacturing function is responsible for guaranteeing that design specifications are adhered to during production and that the final product performs as intended. Thus, for production personnel, quality is described by the manufacturing-based definition. Conformance to product specifications is their goal. The production distribution cycle is completed when the product has been moved from the manufacturing plant, perhaps through wholesale and retail outlets, to the customer. Distribution does not end the customer's relationship with the manufacturer, however. The customer may need various services such as installation, user information, and special training. Such services are part of the product and cannot be ignored in quality management. The American National Standard Institute and the American Society for Quality standardized official definitions of quality terminology in 1978. These groups defined quality as the totality of features and characteristics of a product or service that bears on its ability to satisfy given needs. This definition draws heavily on the product and user-based approaches and is driven by the need to contribute value to customers and thus to influence satisfaction and preference. By the end of the 80s, many organizations had begun using a simpler yet powerful customer-driven definition of quality that remains popular today. Quality is meeting or exceeding customer expectations. To understand this definition, one must first understand the meanings of customer. Most people think of a customer as the ultimate purchaser of a product or service. For instance, the person who buys an automobile for personal use or the guest who registers at a hotel is considered an ultimate purchaser. These customers are more precisely referred to as consumers. Clearly meeting the expectations of consumers is the ultimate goal of any business. Before a product reaches consumers, however, it may flow through a chain of many firms or departments, each of which adds some value to the product. For example, an automobile engine plant may purchase steel from a steel company, produce engines, and then transport the engines to an assembly plant. The steel company is a supplier to the engine plant is a supplier to the assembly plant. The engine plant is thus a customer of the steel company, and the assembly plant is a customer of the engine plant. These customers are called external customers. Every employee in an organization also has internal customers who receive goods or services from suppliers within the organization. An assembly department, for example, is an internal customer of the machining department, and managers are internal customers of the secretarial pool. Most businesses consist of many such chains of customers. Thus, the job of an employee is not simply to please his or her supervisor. It is to satisfy the needs of particular internal and external customers. Failure to meet the needs and expectations of internal customers can result in a poor quality product. For example, a poor design for a computerized hotel reservation system makes it difficult for reservation clerks to do their job and consequently affects consumer satisfaction. Identifying who one's customers are and understanding their expectations are fundamental to achieving customer satisfaction. This focus is a radical departure from traditional ways of thinking in a functionally oriented organizations. It allows workers to understand their place in the larger system and their contribution to the final product. Principles are the foundation of the philosophy. Practices are activities by which the principles are implemented, and techniques are tools and approaches that help managers and employees make the practices effective. All must work together. Total quality is based on three fundamental principles: a focus on customers and stakeholders, employee engagement and teamwork by everyone in the organization, a process focus supported by continuous improvement and learning. Despite their obvious simplicity, these principles are quite different from traditional management practices. Historically, firms did little to understand external customer requirements, much less those of internal customers. Managers and specialists controlled and directed production systems. Workers were told what to do and how to do it, and rarely were asked for their input. Employee engagement and teamwork were virtually non-existent. A certain amount of waste and error was tolerable and was controlled by post-production inspection. Improvements in quality generally resulted from technological breakthroughs instead of a relentless mindset of continuous improvement. With total quality, an organization actively seeks to identify customer needs and expectations, to build quality into work processes by tapping the knowledge and experience of its workforce, and to continually improve every facet of the organization. Now let's examine each of these principles. Customer and stakeholder focus. The customer is the principal judge of quality. Perceptions of value and satisfaction are influenced by many factors throughout the customer's overall purchase, ownership, and service experiences. To accomplish this task, an organization's efforts need to extend well beyond merely meeting specifications, reducing defects and errors, or resolving complaints. They must include both designing new products that truly delight the customer and responding rapidly to changing consumer and market demands. An organization that is close to its customer knows what the customer wants, how the customer uses its products, and anticipates needs that the customer may not even be able to express. It also continually develops new ways of enhancing customer relationships. A firm also must recognize that internal customers are as important in assuring quality as are external customers who purchase the product. Employees who view themselves as both customers and suppliers to other employees understand how their work links to the final product. After all, the responsibility of any supplier is to understand and meet customer requirements in the most efficient and effective way possible. Customer focus extends beyond the consumer and internal customer relationships, however. Employees and society represent important stakeholders. An organization's success depends on the knowledge, skills, creativity, and motivation of its employees and partners. Therefore, a total quality organization must demonstrate commitment to employees, provide opportunities for development and growth, provide recognition beyond normal compensation systems, share knowledge, and encourage risk-taking. Viewing society as a stakeholder is an attribute of world-class organization. Business ethics, public health and safety, the environment and community, and professional support are necessary activities that fall under social responsibility. Employee engagement and teamwork. Joseph Juran credited Japanese managers' full use of the knowledge and creativity of the entire workforce as one of the reasons for Japan's rapid quality achievement. When managers give employees the tools to make good decisions and the freedom and encouragement to make contributions, they virtually guarantee that better quality products and production processes will result. Employees who are allowed to participate both individually and in teams in decisions that affect their jobs and the customer can make substantial contributions to quality. This attitude represents a profound shift in the typical philosophy of senior management. The traditional view was that the workforce should be managed, or to put it less formally, the workforce should leave their brains at the door. Good intentions alone are not enough to encourage employee involvement. Management's task includes formulating the systems and procedures and then putting them in place to ensure that participation becomes a part of the culture. Empowering employees to make decisions that satisfy customers without constraining them with bureaucratic rules shows the highest level of trust. Another important element of total quality is teamwork, which focuses attention on customer-supplier relationships and encourages the involvement of the total workforce in attacking systematic problems, particularly those that cross functional boundaries. Traditionally, organizations were integrated vertically by linking all the levels of management in a hierarchical fashion. Total quality requires horizontal coordination between organizational units, such as between design and engineering, engineering and manufacturing, manufacturing and shipping, shipping and sales. Cross-functional teams provide this focus. Partnerships with unions, customers, suppliers, and education organizations also promote teamwork and permit the blending of an organization's core competencies and capabilities with the complementary strengths of partners, creating mutual benefits. For example, many organizations seek suppliers that share their own values. They often educate them in methods of improvement. If suppliers improve, then so will they. Process focus and continuous improvement. The traditional way of viewing an organization is by surveying the vertical dimension, by keeping an eye on an organization chart. However, work gets done or fails to get done horizontally or cross-functionally, not hierarchically. A process is how work creates value for customers. We typically think of processes in the context of production, the collection of activities and operations involved in transforming inputs, physical facilities, materials, capital, equipment, people, and energy into outputs, products, and services. Common types of production processes include machining, mixing, assembly, filling orders, or approving loans. However, nearly every major activity within an organization involves a process that crosses traditional organizational boundaries. For example, an order fulfillment process might involve a salesperson placing the order, a marketing representative entering it on the company's computer system, a credit check by finance, picking, packaging, and shipping by distribution and logistics personnel, invoicing by finance, and installation by field service engineers. A process perspective links together all necessary activities and increases one's understanding of the entire system, rather than focusing only on a small part. Many of the greatest opportunities for improving organizational performance lie in the organizational interfaces, those spaces between the boxes on an organizational chart. Continuous improvement refers to both incremental changes, which are small and gradual, and breakthrough, or large and rapid improvements. These improvements may take any one of several forms. Enhancing value to the customer through new and improved products and services. Reducing errors, defects, waste, and their related costs. increasing productivity and effectiveness in the use of all resources, and improving responsiveness and cycle time performance for such processes as resolving customer complaints or new product introduction. Thus, response time, quality, and productivity objectives should be considered together. A process focus supports continuous improvement efforts by helping to understand these synergies and to recognize the true sources of problems. Real improvement depends on learning, which means understanding why changes are successful through feedback between practices and results, leading to new goals and approaches. A learning cycle consists of 4 stages: planning, execution of plans, assessment of progress, and revision of plans based upon assessment findings. The concept of organizational learning is not new. It has its roots in general systems theory and systems dynamics, developed in 90s and 60s, as well as theories of learning from organizational psychology. Peter Senge has become the major advocate of the learning organization movement. He defines the learning organization as an organization that is continually expanding its capacity to create its future. For such an organization, it's not enough merely to survive. Survival learning, or what is more often termed adaptive learning, is important. Indeed, it is necessary. But for a learning organization, adaptive learning must be joined by generative learning, learning that enhances our capacity to create. The conceptual framework behind this definition requires an understanding and integration of many of the concepts and principles that are part of the total quality philosophy. Senge repeatedly points out, over the long run, superior performance depends on superior learning. Continuous improvement and learning should be a regular part of daily work, practiced at personal, work unit, and organizational levels, driven by opportunities to affect significant change and focused on sharing throughout the organization. Total quality practices can be classified into 6 basic areas of management that are generic to any organization: leadership, strategic planning and design of organizational and work systems, customer engagement and knowledge acquisition, workforce management, process management, information and knowledge management. These areas represent the focus of sections 4 to 8 in the training. Some examples of total quality practices are ensuring that complaints are resolved effectively and promptly, a customer engagement practice; setting organizational vision and values, a leadership practice; allocating resources to support action plans, a strategic planning practice; gathering employee satisfaction data, a workforce management practice; coordinating design and production delivery processes to ensure trouble-free introduction and delivery of products and services, a process management practice; and reviewing and analyzing organizational performance, an information and knowledge management practice. As we will see in section 3, the Malcolm Baldrige criteria for performance excellence provides a framework for such total quality practices. Total quality techniques include a wide variety of tools and statistical methods to plan work activities, collect data, analyze results, monitor progress, and solve problems. For instance, a chart showing trends in manufacturing defects as worker progress through a training program is a simple tool to monitor the effectiveness of the training. The statistical technique of experimental design is often used in product development activities. Throughout the course, we will introduce many techniques that are useful in quality planning, control, and improvement activities. Competitive advantage denotes a firm's ability to achieve market superiority. In the long run, a sustainable competitive advantage provides above average performance. There are 6 characteristics of a strong competitive advantage. It is driven by customer needs and wants. A firm provides value to its customers that competitors do not. It makes a significant contribution to the success of the business. It matches the organization's unique resources with opportunities in the environment. Not two organizations have the same resources. A good strategy uses the firm's particular resources effectively. It is durable and lasting and difficult for competitors to copy. A superior research and development department, for example, can consistently develop new products or processes that enable the firm to remain ahead of competitors. It provides a basis for further improvement. It provides direction and motivation to the entire organization. Each of these characteristics relates to quality, suggesting that quality is an important source of competitive advantage. The importance of quality in achieving competitive advantage is demonstrated by the relationship between quality and profitability summarized in the figure. A product's value in the marketplace is influenced by the quality of its design. Improvements in design will differentiate the product from its competitors, improves a firm's quality reputation, and improves the perceived value of the product. These factors allow the firm to command higher prices as well as to achieve a greater market share, which in turn leads to increased revenues that offset the costs of improving the design. Improved conformance in production or service delivery leads to lower costs through savings in rework, scrap, resolution of errors, and warranty expenses. It is vital to focus quality improvement efforts on both design and conformance. Many organizations simply confine their quality efforts to one dimension. For example, they might focus on defect elimination but fail to design products that customers really want, or they design great products that are plagued with defects and service errors. In today's global marketplace, high conformance is considered entry into the game rather than a source of competitive advantage. Quality is simply the foundation for achieving competitive advantage. Competitive success in today's market depends on such attributes as the speed of new product development, flexibility in production and delivery, and extraordinary customer service. An organization that is committed to total quality must apply it at three levels: the organizational level, the process level, and the performer job level. At the organizational level, quality concerns center on meeting external customer requirements. An organization must seek customer input on a regular basis. Questions such as the following help to define quality at the organizational level. Which products and services meet your expectations? Which do not? What products or services do you need that you are not receiving? Are you receiving products or services that you do not need? Customer-driven performance standards should be used as basis for goal setting, problem solving, performance appraisal, incentive compensation, non-financial rewards, and resource allocation. At the process level, organizational units are classified as functions or departments, such as marketing, design, product development, operations, finance, purchasing, billing, and so on. Because most processes are cross-functional, the danger exists that managers of particular organizational units will try to optimize the activities under their control, which can sub-optimize activities for the organization as a whole. At this level, managers must ask questions such as the following: what products or services are most important to the external customer? What processes produce those products and services? What are the key inputs to the process? Which processes have the most significant effect on the organization's customer-driven performance standards? Who are my internal customers and what are their needs? At the performer level, sometimes called the job level or the task design level, standards for output must be based on quality and customer service requirements that originate at the organizational and process levels. These standards include requirements for such things as accuracy, completeness, innovation, timeliness, and cost. For each output of an individual job, one must ask what is required by the customer, both internal and external. How can the requirements be measured? What is the specific standard for each measure? Viewing an organization from this perspective clarifies the roles and responsibilities of all employees in pursuing quality. Top managers must focus attention at the organizational level. middle managers and supervisors at the process level, and all employees must understand quality at the performer level. Getting everyone involved is the foundation of total quality. Today, organizations are asking employees to take more responsibility for acting as the point of contact between the organization and the customer, to be team players, and to provide more effective and efficient customer service. Such behaviors reflect the personal values and attitudes of individuals. Employees who embrace quality as a personal value often go beyond what they are asked or normally expected to do in order to reach a difficult goal or provide extraordinary service to a customer. Unless quality is internalized at the personal level, it will never become rooted in the culture of an organization. Thus, quality must begin at a personal level, and that means you. Personal quality is an essential ingredient to make quality happen in the workforce. Yet, most organizations have neglected it for a long time. Perhaps management in particular operates under the idea to improving quality is something that organizations do to employees rather than something they do with employees. Let's start with the first lecture in the course Quality Costs. Over the past 20 years, companies have made significant strides in improving quality. Even so, much remains to be done. The cost of quality can be substantial and a source of significant savings. Quality has become an important competitive issue for both service and manufacturing organizations. The ability of some companies to sell higher quality products at lower prices has cost many other firms market share. In an effort to combat this stiff competition, companies have increasingly paid more attention to quality and productivity, especially given the potential to reduce costs and improve product quality simultaneously. As companies implement quality improvement programs, a need arises to monitor and report on the progress of these programs. Managers need to know what quality costs are and how they are changing over time. Reporting and measuring quality performance is absolutely essential to the success of an ongoing quality improvement program. A fundamental prerequisite for this reporting is measuring the costs of quality. But to measure those costs, an operational definition of quality is needed. Defining quality. Quality is often referred to as the degree or grade of excellence. Operationally, a quality product or service is one that meets or exceeds customer expectations. Customer expectations relate to attributes such as product performance, reliability, durability, and fitness for use. A quality specification is the specific level of performance planned for a given quality attribute. Customers expect a quality product or service to perform according to specifications. Quality of conformance is a measure of how a product meets its specifications. Conformance is strongly emphasized because it is the key to meeting customer expectations. In fact, most quality experts believe that quality is conformance is the best operational definition of quality. A defective product is one that does not conform to specifications. Zero defects means that all products conform to specifications. But what is meant by conforming to specifications? Traditional conformance defines an acceptable range of values for each specification or quality characteristic. A target value is defined and upper and lower limits are set that describe acceptable product variation for a given quality characteristic. Any unit that falls within the limits is deemed non-defective. On the other hand, the robust quality view of conformance emphasizes exactness of conformance. Robustness means exact conformance to the target value, no tolerance allowed. There is no range in which variation is acceptable. A non-defective machine part in the robust setting would be one that has a drilled hole that measures exactly 2 inches. Since evidence exists that product variation can be costly, the robust quality definition of conformance is superior to the traditional definition. Defining quality cost. Quality-linked activities are those activities performed because poor quality may or does exist. The costs of performing these activities are referred to as costs of quality. Thus, costs of quality are the costs that exist because poor quality may or does exist. This definition implies that quality costs are associated with two subcategories of quality-related activities: control activities and failure activities. Control activities are performed by an organization to prevent or detect poor quality, because poor quality may exist. Thus, control activities are made up of prevention and appraisal activities. Control costs are the costs of performing control activities. Failure activities are performed by an organization or its customers in response to poor quality. Poor quality does exist. If the response to poor quality occurs before delivery of a bad, non-conforming, unreliable, not durable, and so on product to a customer, the activities are classified as internal failure activities. Otherwise, they are classified as external failure activities. Failure costs are the costs incurred by an organization because failure activities are performed. Notice that the definition of failure activities and failure costs imply that customer response to poor quality can impose costs on an organization. The definitions of quality-related activities also imply four categories of quality costs: prevention costs, appraisal costs, internal failure, and external failure costs. Let's explore each one of them. Prevention costs are incurred to prevent poor quality in the products or services being produced. As prevention costs increase, we would expect the cost of failure to decrease. Examples of prevention costs are quality engineering, quality training programs, quality planning, reporting, supplier evaluation and selection, quality audits, quality circles, and so on. Appraisal costs are incurred to determine whether products and services are conforming to their requirements or customer needs. Examples include inspecting and testing materials, packaging inspection, supervising appraisal activities, product acceptance, process acceptance, measurement, equipment, and outside endorsement. Let's explain several terms here. Product acceptance involves sampling from batches or finished goods to determine whether they meet an acceptable quality level. If so, the goods are accepted. Process acceptance involves sampling goods while in process to see if the process is in control and producing non-defective goods. If not, the process is shut down until corrective actions can be taken. The main objective of the appraisal function is to prevent non-conforming goods from being shipped to customers. Internal failure costs are incurred because products and services do not conform to specifications or customer needs. This non-conformance is detected prior to being shipped or delivered to outside parties. These are the failures detected by appraisal activities. Examples of internal failure costs are scrap, rework, downtime, reinspection, retesting, and design changes. These costs disappear if no defects exist. External failure costs are incurred because products and services fail to conform to requirements or satisfy customer needs after being delivered to customers. Of all the costs of quality, this category can be the most devastating. Costs of recalls, for example, can run into the hundreds of millions. Other examples include lost sales because of poor product performance, returns and allowances because of poor quality, warranties, repairs, product liability, customer dissatisfaction, lost market share, and complaint adjustment. External failure costs, like internal failure costs, disappear if no defects exist. Here is a summary of the four quality cost categories and lists specific examples of costs. Each of the costs could have been expressed as the cost of quality-related activities, such as the cost of certifying vendors, inspecting incoming materials, adjusting complaints, etc. Let's continue with quality cost measurement. Quality costs can also be classified as observable or hidden. Observable quality costs are those that are available from an organization's accounting records, and hidden quality costs are opportunity costs resulting from poor quality. Opportunity costs are not usually recognized in accounting records. Consider, for example, all the examples of quality costs listed and shown in the previous lecture. With the exception of lost sales, customer dissatisfaction, and lost market share, all the quality costs are observable and should be available from the accounting records. Note also that the hidden costs are all in the external failure category. These hidden quality costs can be significant and should be estimated. Although estimating hidden quality cost is not easy, there are three methods that have been suggested: the multiplier method, the market research method, and the Taguchi quality function. Let's explore each method. The multiplier method. The multiplier method assumes that the total failure cost is simply some multiple of measured failure costs. Here is the formula, where K is the multiplier effect. The value of K is based on experience. For example, Westinghouse Electric reports a value of K between 3 and 4. Thus, if the measured external failure costs are $3 million, the actual external failure costs are between $9 million and $12 million. Including hidden costs in assessing the amount of external failure costs allows management to more accurately determine the level of resource spending for prevention and appraisal activities. Specifically, with an increase in failure costs, we would expect management to increase its investment in control costs. The market research method. Formal market research methods are used to assess the effect of poor quality on sales and market share. Customer service and interviews with members of a company's sales force can provide significant insights into the magnitude of a company's hidden costs. Market research results can be used to project future profit losses attributable to poor quality. Next method is the Taguchi quality loss function. The traditional zero defects definition assumes that hidden quality costs exist only for units that fall outside the upper and lower specification limits. The loss function assumes that any variation from the target value of a quality characteristic causes hidden quality costs. Furthermore, the hidden quality costs increase quadratically as the actual value deviates from the target value. The Taguchi quality loss function, illustrated in this picture, can be described by the following equation. The picture here demonstrates that the quality cost is zero at the target value and increases symmetrically at an increasing rate, as the actual value varies from the target value. Assume, for example, that a company produces watches, and the quality characteristic is accuracy as measured by how much time is gained or lost in 3 months. Assume that K equals $2 and T 0 minutes. This picture here illustrates the computation of the quality loss for 4 units. Notice that the cost quadruples when the deviation from target doubles, units 2 and 3. Notice also that the average deviation squared and the average loss per unit can be computed. These averages can be used to compute the total expected hidden quality costs for a product. If, for example, the total units produced are 5,000 and the average squared deviation is 7.5, then the expected cost per unit is 15, 7.5 multiplied by $2, and the total expected loss for the 5,000 units would be $75,000, $15 multiplied by 5,000. To apply the Taguchi loss function, K must be estimated. The value for K is computed by dividing the estimated cost at one of the specification limits by the squared deviation of the limit from the target value. Here is the formula. This means that we still must estimate the loss for a given deviation from the target value. The first two methods, the multiplier method or the market research method, may be used to help in this estimation, a one-time assessment need. Once K is known, the hidden quality cost can be estimated for any level of variation from the target value. Quality costs reporting. A quality cost reporting system is essential if an organization is serious about improving and controlling quality costs. The first and simplest step in creating such a system is assessing current actual quality costs. A detailed listing of actual quality costs by category can provide two important insights. First, it reveals the magnitude of the quality costs in each category, allowing managers to assess their financial impact. And second, it shows the distribution of quality costs by category, allowing managers to assess the relative importance of each category. Quality cost reports. The financial significance of quality costs can be assessed more easily by expressing these costs as a percentage of actual sales. This example here reports the quality costs for a company for a fiscal 2007. According to the report, quality costs represent 20% of sales. Given the rule of thumb that quality costs should be no more than 2 to 4%, this company has ample opportunity to improve profits by decreasing quality costs. Understand, however, that reduction in costs should come through improvement of quality. Reduction of quality costs without any effort to improve quality could prove to be a disastrous strategy. Additional insight concerning the relative distribution of quality costs can be realized by constructing charts that show the relative amount of costs in each category. This example here provides a bar graph and pie chart that show each category's percentage contribution to total quality costs. The graphs reveal that failure costs are approximately 82% of the total quality costs, suggesting that the company has ample opportunity to improve quality and lower total quality costs. Distribution of quality costs. The acceptable quality view. One view of optimal quality cost distribution is the acceptable quality view. Although this view is no longer widely accepted, it serves as a useful point of reference for understanding the current views on how quality costs should be distributed. According to the acceptable quality view, there is an optimal trade-off between failure and control costs. As control costs increase, failure costs should decrease. As long as the decrease in failure costs is greater than the corresponding increase in control costs, a company should continue increasing its efforts to prevent or detect non-conforming units. Eventually, a point is reached at which any additional increase in this effort costs more than the corresponding reduction in failure costs. This point represents the minimum level of total quality costs. It is the optimal balance between control costs and failure costs and defines what is known as the acceptable quality level. The theoretical relationship is illustrated in this picture. The graph reveals that the total quality costs decrease as quality improves up to a point. After that, no further improvement is possible. Thus, acceptable quality level identifies an optimal level of defective units. Note that this level does not correspond to that of zero defects. Distribution of quality costs, zero defects view, and robust quality view. The acceptable quality level view permitted and, in fact, encouraged the production of a given number of defective units. This model prevailed in the quality control world until the late 70s, when the accepted quality level model was challenged by the zero defects model. Essentially, the zero defects model made the claim that it was cost beneficial to reduce non-conforming units to zero. Firms producing increasingly fewer non-conforming units became more competitive relative to firms that continued with the traditional acceptable quality level model. In the mid-80s, the zero defects model was taken one step further by the robust quality model, which challenged the definition of a defective unit. According to the robust view, a loss is experienced from producing products that vary from a target value. The greater the distance from the target value, the greater the loss. In other words, variation from the ideal is costly, and specification limits serve no useful purpose and in fact may be deceptive. The zero defects model understates the quality costs and thus the potential for savings from even greater efforts to improve quality. Therefore, the robust quality model tightened the definition of a defective unit, refined our view of quality costs, and intensified the quality race. This example here shows a quality cost function consistent with the robust quality view. Essentially, what happens is that as firms increase their prevention and appraisal costs and reduce their failure costs, they discover that they can then cut back on their prevention and appraisal costs. What initially appears to be a trade-off turns out to be a permanent reduction in costs for all quality cost categories. There are some key differences. First, control costs do not increase without limit as a robust zero-defect state is approached. And second, control costs may increase and then decrease as the robust state is approached. Third, failure costs can be driven to zero. Suppose, for example, that a firm has decided to improve the quality of its products by re-engineering its manufacturing processes. The objective is to identify ways of producing products that have less chance of being defective. As the firm works to implement this program, additional costs may be incurred. For example, special studies, consulting fees, and hiring of additional process design engineers, and so on. Initially, other prevention and appraisal costs may continue at their current level. However, once the program is fully implemented and evidence is surfacing that the failure costs are being reduced, for example, less rework, fewer customer complaints, and fewer repairs, then the company may decide to cut back on inspections of product, customer complaint departments, and so on. The net effect is a reduction in all quality cost categories, and quality has increased. The role of activity-based cost management. Activity-based costing can be used to calculate the quality cost per unit of a firm's products. Once an ABC system is in place, the only requirement is to identify those activities that are quality related, such as inspection, rework, and warranty work. Assume, for example, that the cost of the rework activity is $250,000. Now assume that a company produces 10,000 units each of two products, a regular model and a deluxe model. The number of units reworked is 1,000 for the regular model and 4,000 for the deluxe model. Units reworked is the activity driver. The activity rate is $50 per reworked unit, and the rework costs and internal failure costs assigned to each product are $50,000 for the regular and $200,000 for the deluxe model. This provides a signal that the deluxe model is of lower quality than the regular model. Thus, ABC can be used as a means to identify cost objects with quality problems, such as low quality products, low quality processes, and low quality suppliers. This can then allow more focused management of quality costs. Activity-based management is also useful. It classifies activities as value-added and non-value-added and keeps only those that add value. This principle can be applied to quality-related activities. Appraisal and failure activities and their associated costs are non-value-added and should be eliminated. Prevention activities performed efficiently can be classified as value-added and should be retained. Root causes or cost drivers can also be identified, especially for failure activities, and used to help managers understand what is causing the costs of the activities. This information can then be used to select ways of reducing quality costs. In effect, activity-based management supports the robust zero-defect view of quality costs. There is no optimal trade-off between control and failure costs. The latter are non-value-added costs and should be reduced to zero. Some control activities are non-value added and should be eliminated. Other control activities are value added but may be performed inefficiently, and the costs caused by the inefficiency are non-value added. Thus, costs for these categories may also be reduced to lower levels. Quality costs and decision making. Reporting quality costs can improve managerial planning, control, and decision making. For example, if a company wants to implement a process reengineering program to improve the quality of its products, it will need to assess the following: current quality costs by item and by category, the additional costs associated with the program, and the projected savings by item and by category. When the costs and savings will occur must also be projected. Then, a capital budgeting analysis can be done to determine the merits of the proposed program. If the outcome is favorable and the program is initiated, then it becomes important to monitor the program through performance reporting. Using quality cost information to implement and monitor the effectiveness of quality programs is only one use of a quality cost system. Other important uses can also be identified. Quality cost information is an important input to management decision making. Decision making context. Managers need quality cost information in a number of decision making contexts. Two of these contexts are strategic pricing and cost volume profit analysis. Strategic pricing. Consider ABC company, which produces electronic measurement devices. Market share for the company's low-level electronic measurement instruments had been steadily dropping. Linda, the marketing manager, identified price as the major problem. She knew that Japanese firms produced and sold the low-level instruments for less than ABC could. If ABC reduced its price to that of the competition, the new price would be below cost. Yet, if something were not done, the Japanese firms would continue to expand their market share. One possibility was simply to drop the low-level line and concentrate on instruments in the medium and high-level categories. Linda knew, however, that this was a short-term solution, since soon the same Japanese firms would be competing at the higher levels. A brief income statement for the low-level instruments is shown here. Linda strongly believed that a 15% price decrease would restore the instrument line's market share and profitability to its former levels. One possibility was the implementation of total quality management. Her first action was to request information on the quality costs for the lower level instruments. ABC controller Emma admitted that the costs were not tracked separately. For example, the cost of scrap was buried in the work in process inventory account. He did promise, however, to estimate some of the costs. Data from his report for the low-level instruments is shown here. Upon receiving the report, Linda, Emma, and Art, manager of the quality control department, met to determine possible ways of reducing quality costs for the low-level line. Art was confident that the quality costs could be reduced by 50% within 18 months. He had already begun planning the implementation of a new quality program. Linda calculated that a 50% reduction in the quality costs associated with the low-level instruments would reduce cost by about $1.60 per unit, which would make up slightly more than half of the $3 reduction in selling price that would be needed. The reduction is 15% of $20. Based on this outcome, Linda decided to implement the price reduction in 3 phases: a $1 reduction immediately, a $1 reduction in 6 months, and the final reduction of $1 in 12 months. This phased reduction would likely prevent any further erosion of market share and would start increasing market share sometime in the second phase. By phasing in the price reductions, the quality control department would have time to reduce costs so that any big losses could be avoided. This example illustrates that both quality cost information and the implementation of a total quality control program contributed to a significant strategic decision. It also illustrates that improving quality was not a panacea. The reductions were not as large as needed to bear the full price reduction. Other productivity gains will be needed to ensure the long-range viability of the product line. Cost volume profit analysis and strategic design decisions. Traditionally, cost volume profit analysis relies on the analysis of fixed and variable costs in conjunction with cost. Terry, the marketing manager, and Sharon, the design engineer, discovered shortcomings in the traditional analysis when they proposed a new product. They had been certain that a proposal for the new product was going to be approved. Instead, they received the following report from the controller's office. In an effort to discover just why the cost figures came out so poorly for a project that both individuals felt strongly would be profitable, the two met with Bob Brown, the assistant controller. Here is the conversation that took place between those people. They wanted to know why there is a $3 per unit scrap cost. And Bob explained that it's based on the scrap cost that we tracked for existing and similar products. Sharon said that she thinks that they have overlooked the new design features of this new product. Its design virtually eliminates any waste, especially when it is considered that the product will be made on a numerically controlled machine. And Terry said that this $2 per unit charge for repair work should be eliminated. The new design that Sharon is proposing solves the failure problems they have had with related products. It also means that the $100,000 of fixed costs associated with the repair center can be eliminated. And Bob asked how certain they are that this new design will eliminate some of these quality problems. Sharon said that it's absolutely certain, that the early prototypes did exactly as they expected. The results of those tests are included in the proposal. And Bob said right, reducing the variable cost by $5 per unit and the fixed cost by $100,000 produces a break-even point of 36,000 units. These changes alone make the project viable, and they will change the report to reflect a positive recommendation. This scenario illustrates the importance of further classifying quality cost by behavior. Although one unit-based behavior is assumed, activity-based classification is also possible and could enhance the decision usefulness of quality cost. The scenario also reinforces the importance of identifying and reporting quality cost separately. The new product was designed to reduce its quality costs, and only by knowing the quality costs assigned could Sharon and Terry have discovered the error in the break-even analysis. Finally, notice the effect total quality management has on design decisions. By being aware of the quality costs and their causes, the new product's design was structured to avoid many of the existing quality problems. Six Sigma began as a manufacturing focus to reduce defect levels to only a few parts per million. It has evolved into a formal business strategy designed to accelerate improvements in every facet of an organization. Six Sigma represents a quality level of at most 3.4 defects per million opportunities, or 3.4 DPMO. The figure explains the theoretical basis for Six Sigma in the context of manufacturing specifications. Motorola chose this figure because field failure data suggested that Motorola's processes drifted by this amount on average. The allowance of a shift in the distribution is important because no process can be maintained in perfect control. Many common statistical process control plans are based on sample sizes that only allow detection of shifts of about 2 standard deviations. Thus, it would not be unusual for a process to drift this much and not be noticed. The area under the shifted curves beyond the Six Sigma ranges, the tolerance limits, is only 3.4 parts per million. Thus, if the process mean can be controlled to within 1.5 standard deviations of the target, a maximum of 3.4 defects per million can be expected. If it is held exactly on target, only 2 defects per billion would be expected. In a similar fashion, we could define 3 sigma quality, 5 sigma quality, and so on. The easiest way to understand it is to think of the distance from the target to the upper or lower specification, half the tolerance, measured in terms of standard deviations of the inherent variation as the sigma level. Let's examine some Six Sigma basic calculations. Some definitions first. Unit is the item produced or processed, either a product or service transaction. Defect is any event that does not meet the specifications or customer requirements. For this method, defects or non-defects must be at least 5. Defect opportunity, any event which can be measured that provides a chance of not meeting customer requirements. Defective is a unit with one or more defects. First time yield exclusive of rework at a process step. And some guidelines, there may be more than one defect opportunity per unit. The opportunity for defect must be important to the customer. Some defects may cause others, only count the original defect as an opportunity. Some examples here. If the unit is invoice, the defect might be incorrect fields identified by the customer. Opportunity, the fields on the invoice. Customer phone call not answered within 30 seconds. Opportunity, each customer call. How to calculate defects per million opportunity? First, we need the number of units processed. Second, the total number of defects made. Include defects made and later fixed. Number of defect opportunities per unit. Solve for DPMO. Here is the formula. And last, we need to look at process sigma in an abridged sigma conversion table. And here is a real example. A company that pays its employees on the 5th of the month has collected data on the number of checks that are received by the employee after the required date. And here are the calculations. The number of units processed, employee checks, here is 1000. Total number of defects made, 356. These are the checks received after the 5th of the month. Number of defect opportunities per unit is 1, it's each check. And when we solve for defects per million opportunities, we receive 356,000 defects per million opportunities. And now we need to look at process sigma in an abridged sigma conversion table. Here is the table, and you can see that for approximately 356,000 we have 1.9 sigma, which is the process sigma in this case. The principal problem solving methodology used by Six Sigma is the make, define, measure, analyze, improve, and control. Define phase. After a Six Sigma project is selected, the first step is to clearly define the problem. This activity is significantly different from project selection. Project selection generally responds to symptoms of a problem and usually results in a rather vague problem statement. One must describe the problem in operational terms that facilitate further analysis. For example, a firm might have a history of poor reliability of electric motors it manufactures, resulting in a Six Sigma project to improve motor reliability. A preliminary investigation of warranty and field service repair data might suggest that the source of most problems was brush wear, and more specifically suggest a problem with brush hardness variability. Thus, the problem might be defined as reduce the variability of brush hardness. This process of drilling down to a more specific problem statement is sometimes called project scoping. A good problem statement should also identify customers and the critical to qualities that have the most impact on product or service performance. Describe the current level of performance or nature of errors or customer complaints. identify the relevant performance metrics, benchmark best performance standards, calculate the cost-revenue implications of the project, and quantify the expected level of performance from a successful Six Sigma effort. The define phase should also address such project management issues as what will need to be done by whom and when. Second phase is measure. This phase of the DMAIC process focuses on how to measure the internal processes that impact critical to qualities. It requires an understanding of the causal relationships between process performance and customer value. However, once they are understood, procedures for gathering facts, collecting good data, observation, and careful listening must be defined and implemented. Data from existing production processes and practices often provide important information, as does feedback from supervisors, workers, customers, and field service employees. The first step in any data collection effort is to develop operational definitions for all performance measures that will be used. For example, what does it mean to have on-time delivery? Does it mean within 1 day of the promised time? 1 week, 1 hour? What is an error? Is it wrong information on an invoice, a typographical mistake, or either? Clearly, any data are meaningless unless they are well defined and understood without ambiguity. These guidelines can greatly improve the process of uncovering relevant facts necessary to identify and solve problems. Six Sigma uses the notion of a function in mathematics to portray the relationship between process performance and customer value. Here is this definition. Y depends on X, where Y is the set of critical to qualities and X represents the set of critical input variables that influence Y. For example, Y might represent the time to deliver bags from an airplane to baggage handling and the number of lost bags. X might include the number of baggage handlers, number of trucks, time they are dispatched, barcode scanning accuracy, and so on. The next step is analyze. A major flaw in many problem-solving approaches is a lack of emphasis on rigorous analysis. Too often we want to jump to a solution without fully understanding the nature of the problem and identifying the source of the problem. The analyze phase of DMAIC focuses on why defects, errors, or excessive variation occur, which often result from one or more of the following. A lack of knowledge about how a process works, which is particularly critical if different people perform the process. A lack of knowledge about how a process should work, including understanding customer expectations and the goal of the process. A lack of control of materials and equipment used in a process. Inadvertent errors in performing work. Waste and complexity, which manifest themselves in many ways, such as unnecessary steps in a process and excess inventories. Failure to understand the capability of a process to meet specifications, lack of training, etc. Finding the answers requires identifying the key variables that are most likely to create errors and excessive variation, the root causes. Root cause is identified as that condition of interrelated set of conditions having allowed or caused a defect to occur, which once corrected properly permanently prevents recurrence of the defect in the same or subsequent product or service generated by the process. As with a medical analogy, eliminating symptoms of problems usually provides only temporary relief. Eliminating root causes provides long-term relief. One useful approach for identifying the root cause is the 5 Why technique. This approach forces one to redefine a problem statement as a chain of causes and effects to identify the source of the symptoms by asking why, ideally 5 times. After potential variables are identified, experiments are conducted to verify them. These experiments generally consist of formulating some hypothesis to investigate, collecting data, analyzing the data, and reaching a reasonable and statistically supportable conclusion. Statistical thinking and analysis plays a critical role in this phase. It is one of the reasons why statistics is an important part of Six Sigma training. Other experiments might employ computer simulation techniques. Improve phase. Once the root cause of a problem is understood, the analyst or team needs to generate ideas for removing or resolving the problem and improve the performance measures and critical to qualities. This idea gathering phase is a highly creative activity because many solutions are not obvious. One of the difficulties in this task is the natural instinct to project ideas before thoroughly evaluating them. Most people have a natural fear of proposing a silly idea or looking foolish. However, such ideas may actually form the basis for a creative and useful solution. Effective problem solvers must learn to defer judgment and develop the ability to generate a large number of ideas at this stage of the process, whether practical or not. A number of processes and tools to facilitate idea generation can be used. One of the most popular is brainstorming. With brainstorming, no criticism is permitted, and people are encouraged to generate a large number of ideas through combination and enhancement of existing ideas. Wild ideas are encouraged and frequently trigger other good ideas from somewhere else. After a set of ideas have been proposed, it is necessary to evaluate them and select the most promising. This process includes confirming that the proposed solution will positively impact the key process variables and the critical to qualities, and identifying the maximum acceptable ranges of these variables. Problem solutions often entail technical or organizational changes. Often some sort of decision or scoring model is used to assess possible solutions against important criteria such as cost, time, quality improvement potential, resources required, effects on supervisors and workers, and barriers to implementation such as resistance to change or organizational culture. To implement a solution effectively, responsibility must be assigned to a person or a group who will follow through on what must be done, where it will be done, when it will be done, and how it will be done. Project management techniques are helpful in implementation planning. The control phase focuses on how to maintain the improvements, which includes putting tools in place to ensure that the key variables remain within the maximum acceptable ranges under the modified process. These improvements might include establishing the new standards and procedures, training the workforce, and instituting controls to make sure that improvements do not die over time. Controls might be as simple as using checklists or periodic status reviews to ensure that proper procedures are followed, or employing statistical process control charts to monitor the performance of key measures. One of the most difficult challenges in Six Sigma is the selection of the most appropriate problems to attack. A problem is a deviation between what should be happening and what actually is happening that is important enough to make someone think the deviation ought to be corrected. Research using more than 1,000 published cases describing quality problem-solving activities suggests that virtually every instance of quality problem-solving falls into one of 5 categories. First, conformance problems are defined by unsatisfactory performance by a well-specified system. Users are not happy with system outputs such as quality or customer service levels. Efficiency problems result from unsatisfactory performance from the standpoint of stakeholders other than customers. Typical examples are cost and productivity issues. Unstructured performance problems result from unsatisfactory performance by a poorly specified system. That is, the task is not non-standardized and not fully specified by procedures and requirements. Product design problems involve designing new products that better satisfy user needs, the expectations of customers that matter most to them. Process design problems involve designing new processes or substantially revising existing processes. The challenge here is determining process requirements, generating new process alternatives, and linking these processes to customer needs. A Six Sigma project might span an entire division or be as narrow as a single production operation. Factors that should be considered when selecting Six Sigma projects include the following: financial return as measured by costs associated with quality and process performance and impacts on revenues and market share, impacts on customers and organizational effectiveness, probability of success, impact on employees, and fit to strategy and competitive advantage. As we noted several times in earlier sections, Six Sigma projects are driven by expected financial returns. Reducing costs associated with poor quality, such as scrap, rework, excessive cycle times, delays, and lost customers, often provide an obvious justification for pursuing a project. A cost of quality process often facilitates identifying opportunities and measuring results. Projects chosen should have a high likelihood of success. Considerable risk comes in choosing problems that can best be compared with solving world hunger. At the outset of a Six Sigma initiative, it is beneficial to pick the low-hanging fruit, projects that are easy to accomplish, or even can be completed by a single individual in order to show early successes. This visible success helps to build momentum and support for future projects. Studies show that many projects are significantly over budget, behind schedule, or do not result in desired outcomes. Thus, good project management is essential. Six Sigma projects should fit within the capabilities of the people and teams that work on them. Many indirect benefits accrue. The training received as green or black belts improves employee and organizational knowledge, and participating in Six Sigma projects improves teams and leadership skills. Six Sigma can motivate employees to innovate and improve their work environment, and ultimately their satisfaction on the job and personal self-esteem. Many projects offer opportunities to reduce frustration with inadequate work processes or to provide increased value to customers. These types of projects are certainly important candidates for selection. And finally, Six Sigma projects should support the organization's vision and competitive strategy. At General Electric, for example, business goals work their way down the organization, helping employees to distinguish between projects that will not have a significant effect on business performance and those that do. Among the many tools that comprise the Six Sigma toolbox are 7 simple tools: flowcharts, check sheets, histograms, Pareto diagrams, cause and effect diagrams, scatter diagrams, and control charts. The Japanese call them the 7 quality control tools, and they have been used for decades to support quality improvement efforts. They are designed simply so that workers at all levels can use them easily. We will briefly review each tool to explain its role in quality improvement. Flowcharts. To clearly define a Six Sigma or any process improvement project, one must first understand the process that creates the outputs that internal or external customers receive. This understanding sets the foundation for identifying critical to quality issues, selecting measurements, and identifying root causes of problems, identifying non-value-added steps, and reducing variation. Flowcharts are best developed by having the people involved in the process. Employees, supervisors, managers, and customers construct the flowchart. A facilitator provides objectivity in resolving conflicts. The facilitator can guide the discussion through questions such as what happens next, who makes the decision at this point, and what operation is performed at this point. Quite often the group does not universally agree on the answers to these questions due to misconceptions about the process itself or a lack of awareness of the big picture. Flowcharts can easily be created using Microsoft Excel, Visio, or other programs using the features found on the drawing toolbar. Flowcharts help all employees understand how they fit into a process and who are their suppliers and customers. This realization then leads to improved communication among all parties. By participating in the development of a flowchart, workers feel a sense of ownership in the process and hence become more willing to work on improving it. If flowcharts are used in training employees, more consistency will be achieved. Flowcharts also help to pinpoint places where quality-related measurements should be taken. Once a flowchart is constructed, it can be used to identify quality problems as well as areas for productivity improvement. Questions such as how does this operation affect the customer? Can we improve or even eliminate this operation? Or should we control a critical quality characteristic at this point? Trigger the identification of opportunities. The next tool is a run chart or control chart. A run chart is a line graph in which data are plotted over time. The vertical axis represents a measurement, the horizontal axis is the time scale. The daily newspaper usually includes several examples of run charts, such as the Dow Jones Industrial Average. They can be used to track such things as production volume, costs, and customer satisfaction indexes. The first step in constructing a run chart is to identify the measurement or indicator to be monitored. In some situations, one might measure the quality characteristics for each individual unit of process output. For low-volume processes such as chemical production or surgeries, this approach would be appropriate. However, for high-volume production processes or services with large numbers of customers or transactions, it would be impractical. Instead, samples taken on a periodic basis provide the data for computing basic statistical measures, such as the mean, range, or standard deviation, proportion of items that do not conform to specifications, or number of non-conformances per unit. A control chart is simply a run chart to which two horizontal lines called control limits are added, the upper control limit and lower control limit. Control charts were first proposed by Schuhart and were strongly advocated by Deming. Control limits are chosen statistically to provide a high probability, generally greater than 0.99, that points will fall between these limits if the process is in control. Control limits make it easier to interpret patterns in a run chart and draw conclusions about the state of control. If sample values fall outside the control limits, or if non-random patterns occur in the chart, then special causes may be affecting the process. The process is not stable. The process should be examined and corrective action taken as appropriate. If evaluation and correction are done in real time, then the chance of producing non-conforming product is minimized. Thus, as a problem-solving tool, control charts allow operators to identify quality problems as they occur. Of course, control charts alone cannot determine the source of the problem. Operators, supervisors, and engineers may have to resort to other problem-solving tools to seek the root cause. The next tool is check sheet. Check sheets are simple tools for data collection. Nearly any kind of form may be used to collect data. Data sheets use simple columnar or tabular forms to record data. However, to generate useful information from raw data, further processing generally is necessary. In manufacturing, check sheets are simple to use and easily interpreted by shop personnel. Including information such as specification limits makes the number of non-conforming items easily observable and provides an immediate indication of the quality of the process. The next tool is a histogram. A histogram is a basic statistical tool that graphically shows the frequency or number of observations of a particular value or within a specified group. Some caution should be needed when interpreting histograms. First, the data should be representative of typical process conditions. If a new employee is now operating the equipment or some aspect of the equipment, material, or method has changed, then new data should be collected. Second, the sample size should be large enough to provide good conclusions. The larger, the better. Various guidelines exist, but a suggested minimum of at least 50 observations should be drawn. Finally, Any conclusions drawn should be confirmed through further study and analysis. Pareto diagrams. Joseph Durand popularized the Pareto principle in 1950s after observing that a high proportion of quality issues resulted from only a few causes. He named this technique after Wilfredo Pareto, who determined that 85% of the wealth in Milan was owned by only 15% of the people. For instance, in analyzing costs in a paper mill, Durand found that 61% of total quality costs were attributable to one category, broke, which is paper mill terminology for paper so defective that it is returned for reprocessing. Pareto analysis is often used to analyze data collected in check sheets. Such a visual aid clearly shows the relative magnitude of defects and can be used to identify opportunities for improvement. The most costly or significant problems stand out. Pareto diagrams can also show the results of improvement programs over time. They are less intimidating to employees who are fearful of statistics. Next tool, cause and effect diagrams. Variation in process output and other quality problems can occur for a variety of reasons, such as materials, machines, methods, people, measurement, etc. The goal of problem solving is to identify the causes of problems in order to correct them. The cause and effect diagram is an important tool on this task. It assists the generation of ideas for problem causes and in turn serves as a basis for solution finding. Kaoru Ishikawa introduced the cause and effect diagram in Japan, so it is also called an Ishikawa diagram. Because of its structure, it is often called a fishbone diagram. The general structure of a cause and effect diagram is shown here on the slide. At the end of the horizontal line, a problem is listed. Each branch pointing out the main stem represents a possible cause. Branches pointing to the causes are contributors to those causes. The diagram identifies the most likely causes of a problem so that further data collection and analysis can be carried out. Cause and effect diagrams are constructed in a brainstorming type of atmosphere. Everyone can get involved and feel they are an important part of the problem-solving process. Usually small groups drawn from operations or management work with a trained and experienced facilitator. The facilitator guides attention to discussion of the problem and its causes, not opinions. As a group technique, the cause and effect method requires significant interaction between group members. The facilitator who listens carefully to the participants can capture the important ideas. A group can often be more effective by thinking of the problem broadly and considering environmental factors, political factors, employee issues, and even government policies if appropriate. The last of the 7 tools is scatter diagrams. Scatter diagrams are the graphical component of regression analysis. Even though they do not provide rigorous statistical analysis, they often point to the important relationships between variables, such as the percentage of an ingredient in an alloy and the hardness of the alloy. Typically, the variables in question represent possible causes and effects obtained from Ishikawa diagrams. For example, if a manufacturer suspects that the percentage of an ingredient in an alloy is causing quality problems in meeting hardness specifications, an employee group might collect data from samples on the amount of ingredient and hardness and plot the data on a scatter diagram. Statistical correlation analysis is used to interpret scatter diagrams. There are 3 types of correlation. If the correlation is positive, an increase in variable x is related to an increase in variable y. If the correlation is negative, an increase in x is related to a decrease in y. And if the correlation is close to 0, the variables have no linear relationship. Lean production refers to approaches that originated at the Ford Motor Company but which were refined and modernized by the Toyota Motor Corporation later in the century. Lean approaches focus on the elimination of waste in all forms, including defects requiring rework, unnecessary processing steps, unnecessary movement of materials or people, waiting time, excess inventory, and overproduction. A simple way of defining it is getting more done with less. It involves identifying and eliminating non-value added activities throughout the entire value chain to achieve faster customer response, reduced inventories, higher quality, and better human resources. Lean production is facilitated by a focus on measurement and continuous improvement, cross-trained workers, flexible and increasingly automated equipment, efficient machine layout, rapid setup and changeover, just-in-time delivery and scheduling, realistic work standards, worker empowerment to perform inspections and take corrective action, supplier partnerships, and preventive maintenance. Some of the benefits claimed by proponents of lean production include the following: at least 60% reduction in cycle time, 40% improvement in space utilization, 25% greater throughput, 50% reduction in work in process and finished good inventories, 50% improvement in quality, 20% improvements in working capital and worker productivity. However, as one industry expert observed, it takes an incredible amount of detailed planning, discipline, hard work, and painstaking attention to detail. Surveys have noted that mid-sized and large companies are likely to be familiar with lean principles and have systems in place. However, few small manufacturing shops have much familiarity with the principles. Thus, considerable opportunity exists for this important economic sector. Some of the key tools used in lean production include the 5 S's. The 5 S's are derived from Japanese terms seiri for sort, seiton for set in order, seiso for shine, seiketsu for standardize, and shitsuke for sustain. They define a system for workplace organization and standardization. Sort refers to ensuring that each item in a workplace is in its proper place or identified as unnecessary and removed. Set in order means to arrange materials and equipment so that they are easy to find and use. Shine refers to a clean work area. Not only is this important for safety, but as a work area is cleaned, maintenance problems such as oil leaks can be identified before they cause problems. Standardize means to formalize procedures and practices to create consistency and ensure that all steps are performed correctly. Finally, sustain means to keep the process going through training, communication, and organizational structures. Visual controls are indicators for tools, parts, and production activities that are placed in plain sight of all workers so that everyone can understand the status of the system at a glance. Thus, if a machine goes down or a part is defective or delayed, immediate action can be taken. Efficient layout and standardized work. The layout of equipment and processes is designed according to the best operational sequence by physically linking and arranging machines and process steps most efficiently, often in a cellular arrangement. Standardizing the individual tasks by clearly specifying the proper method reduces wasted human movement and energy. Pool production. In this system, also described as Kanban, upstream suppliers do not produce until the downstream customer signals a need for parts. Single minute exchange of dies. This refers to rapid changeover of tooling and fixtures in machine shops, so that multiple products in smaller batches can be run on the same equipment. Reducing setup times adds value to the operation and facilitates smoother production flow. Total productive maintenance. Total productive maintenance is designed to ensure that equipment is operational and available when needed. Source inspection. Inspection and control by process operators guarantees that product passed on to the next production stage conforms to specifications. Continuous improvement provides the link to Six Sigma. In order to make lean production work, one must get to the root causes of problems and permanently remove them. Teamwork is an integral part of continuous improvement in lean environments. Lean tools can easily be applied to non-manufacturing environments as well. Pure service firms such as banks, hospitals, and restaurants have benefited from lean principles. In this context, lean production is often called lean enterprise. For example, banks require quick response and efficiency to operate on low margins, making many of their processes, such as check sorting and mortgage approval, natural candidates for lean enterprise solutions. Handling of paper checks and credit card slips, for instance, involves a physical process not unlike an assembly line. The faster a bank moves checks through the system, the sooner it can collect its funds and the better its returns on invested capital. Lean Six Sigma. Six Sigma is a useful and complementary approach to lean production. For example, a cycle time reduction project might involve aspects of both. Lean tools might be applied to streamline an order entry process. This application leads to the discovery that significant rework occurs because of incorrect addresses, customer numbers, or shipping charges and results in high variation of processing time. Six Sigma tools might then be used to drill down to the root cause of the problems and identify a solution. Because of these similarities, many practitioners have begun to focus on Lean Six Sigma, drawing upon the best practices of both approaches. Both are driven by customer requirements, focus on real dollar savings, have the ability to make significant financial impacts on the organization, and can easily be used in non-manufacturing environments as well. Both use basic root cause, process, and data analysis techniques. However, some differences clearly exist between lean production and Six Sigma. First, they attack different types of problems. Lean production addresses visible problems in processes, for example, inventory, material flow, and safety. Six Sigma is more concerned with less visible problems, for example, variation in performance. In essence, Lean is focused on efficiency by reducing waste and improving process flow, whereas Six Sigma is focused on effectiveness by reducing errors, defects, and variation. Another difference is that lean tools are more intuitive and easier to apply by anybody in the workplace, whereas many Six Sigma tools require advanced training and expertise of black belt or master black belt specialists or consultant equivalents. For example, the concept of 5 S's is easier to grasp than statistical methods. Thus, organizations might be well advised to start with basic lean principles and evolve toward more sophisticated Six Sigma approaches. However, it is important to integrate both approaches with a common goal: improving business results. Management and planning tools. The tools presented here are used by managers or knowledge workers to organize concepts, ideas, and words. These tools are oriented more toward facilitating management and planning activities. The first one is the activity network diagram. This is a term that includes the critical path method and the program evaluation and review technique. The activity network diagram is used when a task is complex and/or lengthy, and because of schedule constraints, it is desirable to determine which activities can be done in parallel. The activity network diagram shows who is going to do what and when, and arrows are drawn to show what must be done in series and what can be done in parallel, so that action can be taken if the overall time estimate is too high to meet goals. In the activity network diagram shown here, each numbered node represents one task that must be completed as a part of a project. The numbers shown between nodes are estimates of the number of weeks to complete the work in a given activity. The critical path can then be calculated. The critical path is the longest path in the series of activities, those activities that must be completed on time to meet the planned project completion date. Next one is affinity diagram. The affinity diagram is a method used to organize a large group of items into smaller chunks that are easier to understand and deal with. It is often used after a brainstorming process to organize the ideas that were listed. It can be done by first creating categories into which ideas will be placed, or all ideas can first be grouped into what appear to be similar categories that will be named after all grouping is completed. The process can be aided by writing each idea on a sticky note and having members of the group move the notes around until they are satisfied. Some items may also be placed in multiple groups when deemed useful. A major benefit of the affinity diagram is that it creates a discussion as to what the various ideas mean to each individual, and the resulting diagram is a jointly created mental model of the situation being analyzed. Interrelationship diagram. While the affinity diagram organizes and makes visible various ideas about a project, the interrelationship diagram pinpoints logical cause and effect relationships between the ideas. It is often constructed using the components of an affinity diagram by asking if this category were changed, would it impact each of the other categories? When the answer is yes for any pair of categories, an arrow is drawn from the first to the second, showing the cause and effect relationship. Next tool is priority matrix. The priorities matrix assists in choosing between several options that have many useful benefits, but where not all of them are of equal value. The relative merit of each available course of action and the related effects creates a complicated picture that is difficult to prioritize. A priorities matrix is created and used according to the following steps. First, a matrix is created to compare all criteria to be used in making the choice. All criteria are listed on both axes and are then compared and assigned a weighted score, relative raw percent, on the basis of the perceived importance of each criterion relative to each other. Once criteria have been weighted, then all possible choices are rated on how well they compare based on each criterion. A new matrix is required to evaluate the options against each criteria. A final matrix compares possible choices on the left axis and the decision criteria along the top. The appropriate weighted scores from the other matrices are inserted and multiplied to get a score for each option for each criterion. The option achieving the highest raw total is often considered the best overall choice. The priorities matrix can add objectivity to what might otherwise be an emotional decision. When numerous possibilities exist and the selection criteria are many and complicated, this tool allows a group to systematically discuss, identify and prioritize the criteria that should have the most influence on the decision, and then to evaluate all the possibilities while keeping a complete picture in mind. Process Decision Program Chart. No matter how well planned an activity is, things do not always run out as expected. The Process Decision Program Chart, similar to fault tree analysis, can be used to identify contingency plans for several situations that might contribute to failure of a particular project. The tasks to be completed for the project are listed, followed by a list of problems that could occur. For each problem, a decision can be made in advance as to what will be done if each problem does occur. The contingency plan should also include ensuring availability of the resources needed to take action. This figure here shows a process decision program chart, a tool that is especially useful when a process is new, meaning there are no previous data on types and frequencies of failure. The tree diagram breaks down an objective into the more detailed steps that must be carried out in order to achieve the objective. It begins with the broad objective and becomes more specific at each level. Let's now explore some process improvement tools. The first tool is root cause analysis. Although an effort to solve a problem may utilize many of the tools, involve the appropriate people and result in changes to the process, if the order in which the problem-solving actions occur isn't logically organized and systematic, much of the effort is likely to be wasted. In order to ensure that efforts are properly guided, many organizations create or adopt one or more models to be followed. 7-step problem-solving model. Problem solving is about identifying root causes that have caused the problem to occur and taking actions to remove those causes. Following is a typical problem solving process model. Step 1. Identify the problem. This step involves making sure that everyone is focused on the same issue. It may involve analysis of data to determine which problem should be worked on and developing a problem statement that clearly defines the exact problem and where and when it occurred. A flowchart might be used to ensure that everyone understands the process. Step 2. List possible root causes. Before jumping to conclusions about what to do about the problem, it is useful to look at the wide range of possibilities. Brainstorming and cause and effect analysis are often used. Step 3. Seeking the most likely root cause. This stage requires looking for patterns in failure of the process. Check sheets might be used to record each failure and supporting information, or control charts may be used to monitor the process to detect trends or special causes. Step 4. Identify potential solutions. Once it is clear that the particular root cause has been assigned, a list of possible actions to remedy it should be developed. You may rely on brainstorming as well as input from specialists. Step 5. Select and implement a solution. After identifying several possible solutions, each should be evaluated as to its potential for success, cost, and timing for implement. Simple processes such as ranking or more complex analysis using a matrix are likely to be used in the selection process. Step 6. Follow up to evaluate the effect. As with any good corrective action process, it is necessary that the process be monitored after the solution has been implemented. Control charts or Pareto diagrams are tools used to determine whether the problem has been solved. If there was no effect, then the actions taken during the previous steps of the problem-solving model need to be reviewed in order to see where an error may have occurred. Step 7. Standardize the process. Even if the problem has been resolved, there is one final step. The solution should be built into the process so that it will continue to work once focused attention on the problem is gone. 5 whys. Throughout most problem solving, there is usually a significant amount of effort expended in trying to understand why things happened the way they do. Root cause analysis requires understanding how a system or process works and the many complex contributors, both technical and human. One method to getting to root causes is to repeatedly ask why. It is called the 5 whys since it often requires asking why 5 times or more before the actual root cause has been identified. The use of data or trials can help determine answers at each level. The plan-do-check-act cycle was adopted by Deming as the plan-do-study-act cycle, emphasizing the role of learning in improvement. In both cases, action is initiated by developing a plan for improvement, followed by putting the plan into action. In the next stage, the results of the action are examined critically. Did the action produce the desired results? Were any new problems created? Was the action worthwhile in terms of cost and other impacts? The knowledge gained in the third step is acted on. Possible actions include changing the plan, adopting the procedure, rejecting the idea, modifying the process, amplifying or reducing the scope, and then beginning the cycle over again. SIPOC analysis. Problem-solving efforts are often focused on remedying a situation that has developed in which a process is not operating at its normal level. Much of continuous improvement involves improving a process that may be performing as expected, but where a higher level of performance is desired. A fundamental step to improving a process is to understand how it functions from a process management perspective. This can be seen through an analysis to identify the supplier input process output customer linkages. It begins with defining the process of interest and listing on the right side the outputs that the process creates that go to customers who are also listed. Suppliers and what they provide to enable the process, the inputs, are similarly shown on the left side. Once this fundamental process diagram is developed, 2 additional items can be discussed. Measures that can be used to evaluate performance of the inputs and outputs, and the information and methods necessary to control the process. Six Sigma and the Make model. Statistically speaking, sigma is a term indicating to what extent a process varies from perfection. The quantity of units processed divided into the number of defects actually occurring multiplied by 1 million results in defects per million. The higher the process sigma, the more the process outputs, products, and services meet customers' requirements, or the fewer the defects. The term Six Sigma refers to process capability equivalent to produce 3.4 defects per million opportunities. Six Sigma as a philosophy translates to the organizational belief that it is possible to produce totally defect-free products or services, albeit more a dream than a reality for most organizations. With most organizations operating at about 3 Sigma or below, getting to perfection leaves much work to be done. The following list contains fundamental Six Sigma practices and some of the applicable tools commonly known as the Make model. Define the customer and organizational requirements. Data collection tools, check sheets, brainstorming and flowcharts. Data analysis tools, cause and effect diagrams, affinity diagrams, tree diagram, root cause analysis. Customer data collection and analysis, quality function deployment, and service. Measure what is critical to quality. Map the process, establish measurement system, and determine what is unacceptable, defects. Process control tools, control charts, process improvement tools, process mapping, Pareto charts, process benchmarking, risk assessment, theory of constraints, cost of quality, lean techniques. Analyze to develop a baseline, process capability. Identify root causes of defects, pinpoint opportunities, and set objectives. Improve the process, project planning and management, training. Control the system through an established process. Failure mode and effect analysis is used for analyzing designs or processes for potential failure. Its aim is to reduce risk of failure. Therefore, there are two types in general use: the DFMEA for analyzing potential design failures and the PFMEA for analyzing potential process failures. The collaboration with employees who have been involved in design, development, production, execution, and customer service activities is critical because their knowledge, ideas, and questions about a new product process design will be based on their experience at different stages of product realization or process execution. Value stream mapping is a paper and pencil tool that helps you to see and understand the flow of material and information as a product or service makes its way through your production or transactional process. It's a way to evaluate the current process, identify the value added steps, and then to design and implement the future state map which has waste removed. The value stream mapping represents actions taken to bring the product or service into existence from the raw material stage to the finished goods stage. This flowcharting method uses symbols, metrics, and arrows to help visualize processes and track performance. These maps enable everyone, management, the workforce, suppliers, and customers to see value, to differentiate it from waste, and to develop a plan of action for waste elimination. Value stream maps are simple yet logical and powerful representations of the process, the value stream, and they are used to document both the current state, the reality, and future desired state. To me, the most important and crucial part of the method is the recognition that the current state maps are a snapshot of how the value stream was actually operating at a given point in time. The real purpose of mapping is to design and implement the future state. It's a powerful tool, but it's not the full answer. First, clarify the goal and the implementation time frame. Remember, if you don't know where you're going, any road will get you there. Second is scope. Where does it start and where does it end? Is it to be a pilot project within the plant or company, or to be extended out to the supply chain? Third is performance. A value stream map will help you understand the delivery performance, customer satisfaction, and lead time variation. The mapping exercise should be as much about the information flows as about the physical flows. It ties the two together. That is the real benefit. Elements of a basic value stream map. A value stream map is divided into three main elements or sections as shown in this figure: process production flow, information or communication flow, and timelines and travel distances. Let's now take a closer look at each of these elements. The process or production flow. The production flow is the part of the map associated with the movement of materials through the factory. It should always be drawn from left to right and never doubling back on itself. Parallel tasks or subtasks should follow the same pattern beneath the mainstream. This way you will be able to separate the major and minor steps in the process, as well as to see parallel tasks and alternative ways to run the process. Moreover, all the problems and hurdles existing within the current state can be discussed and analyzed by constantly looking for solutions to eliminate waste and improve the entire process. The flow of information tells each process what to make or do next. Material and information flows are two sides of the same coin, and you should map both of them. By adding communication to the map, it becomes possible to see both formal and informal communication and information that exists within the value chain. Much of the waste that appears within a value stream is caused by non-value added communication. Although the main communication stream goes from the customer back to the supplier or from right to left on the page, there is no standardized flow for it. You can see that communication can flow both ways or in any direction. Sometimes several communication channels overlap and generate a lot of waste. At the bottom of the map you see a series of lines providing some of the most important information. These are the timelines which are used to show the primary time data measured in the process. The top line is called the process lead time, production lead time, or just a lead time. This line depicts how it takes on average to transform the raw material to end product. Typically it's measured as the number of days worth work or inventory days work. At the end of the timeline you get the total process lead time. Below this line you see another timeline, value added time. It represents the average time between two consecutive parts coming out of a process that actually transform the part in a way that the customer is willing to pay for. Another line placed at the bottom of many maps is travel distance through the process. It's used to outline the travel distance of the product or work, or the travel distance of the people moving within the process. It is used for physical travel only. The basic icons and symbols used in value stream mapping are a combination of flowcharting icons and shapes which represents various tasks and functions within a map. This figure here shows most of these basic icons. It's a common practice for each company or person to create his or her own icons. The most important part here is to explain the meaning and function of the new icons to the audience. Providing an overall legend might be also useful for people involved in the process. Bear in mind that you can see and use any of these symbols at any time during the mapping exercise. You can download these icons and their meanings from the resource sections of this lecture. In the next several lectures, I'm going to walk you through the value stream mapping process step by step, from selecting the product family through drawing the current and future state map to develop an implementation plan and implement the new future state. In this lecture, we will examine the value stream mapping benefits, some maps and applications, and I will share some tips and good practices. Benefits of value stream mapping tool. Value stream mapping is a paper and pencil tool used to follow the product service and information activity flow from beginning to end and draw a visual representation of every process in both flows. Then a future state map which has waste removed should be designed to end up with a detailed implementation plan and its execution. Value stream mapping is an essential tool, and I would point out the following benefits of deploying it. It helps visualize the entire value stream flow within the organization. It helps us identify the sources of waste. It shows the linkages between material and information flow. It enables broad participation in shaping the future. It provides a common language to talk about processes. It forms the basis of the implementation plan. It ties together other linked concepts and methods. It helps us make sound decisions about the flow based on real data and facts. It describes how activities are being done, and it helps all stakeholders understand their part of the processes. Besides the value stream map I outlined in the previous lectures, there are several other map types that can be used to remove some of its limitations and complement the value stream maps. I have outlined briefly the most used and available types of maps and their applications. The first one is the relationship map. It's a high-level diagram showing the main product flow and stages. It helps you view work at the organizational level and shows the main input-output connections. It serves to clarify the overall logic of a plant. A supply chain version would show you the main suppliers, supply and delivery routes, distribution centers, and main customers. Next type of map is cross-functional process map. Also known as swim lane diagram, it illustrates and follows the workflow in organizations crossing different departments and functions. It shows the boundaries and an entire flow at a glance, highlight internal and external customer touchpoints and the handoffs between the functions within the organization. Flowchart. A flowchart is a graphic representation of the sequence of activities used to create, produce, or provide a specific output. It's much more detailed than any other map. It's a step-by-step description of each task or activity at every process step. Spaghetti diagram. The spaghetti diagram is a long-standing tool for more effective layout. It tracks the waste of motion and transport. To build this map, you need a layout draft of the area, facility, and trace the physical flow of the product. Don't forget to mark the inventory locations, rework loops, and inspection points. Calculate the total length of the flow and travel. Waste movement and poor layout become clearly apparent. The value stream map gives you the logic of the main process steps. This map gives you the geography. Financial maps. It's possible and reasonable to combine value stream mapping with financial aspect to see where the money is tied up. This gets executives' attention more than stock turns. The cost map is simply an extension of the current state map and shows a snapshot of the costs within the value stream. Inventory costs are shown with the respect of raw materials, work in process, and finished goods, and stage-by-stage costs, labor, and machines. The whole supply chain mapping. Seeing the whole supply chain is very similar to value stream mapping, only the scope is greater, the intercompany value stream rather than the in-plant value stream. On this larger map, the process steps are replaced by plants, and some intermediate stages like warehouses and cross-docks are added. The main benefit is to gain an understanding of the complete supply chain and to identify major opportunities. Keep the end customer in mind because waste identification and opportunities are focused on it. Mapping tips and good practices. Value stream mapping can be a tool to help identify and eliminate waste, but it's easy to get lost in the details. These tips will help you keep your eye on the big picture to ensure your value stream mapping remains an effective tool for continuous improvement. Some of them are insights from my own experience, while others I have come across when visiting various conferences, trainings, and researching various articles and materials. First, always collect current state information while walking the actual pathways of material and information flow yourself. Capture the process as it operates now, not how it is supposed to operate. Begin with a brisk walk through the entire value stream to get a sense of the big picture and the layout of the processes. Begin at the customer end and follow the flow upstream. This way, you will catch the processes directly linked to the customer, which should set the pace for the whole value stream. Always draw by pencil. Don't use your computer. Draw your rough draft on the shop floor, not in the office on your computer. Map the value stream yourself in order to understand the entire flow. Do not rely on standard times, measures, averages, etc. Bring your stopwatch and ruler if you want to project an accurate future state. Draw the material flow from left to right on the bottom half of the map in the order of processing steps, not according to the layout of the facility. Information flow is drawn from right to left in the top half of the map. When designing your future state, strive to synchronize the pace of production with the pace of sales at the pacemaker process. Value stream improvement is management's responsibility. Assign a value stream manager to lead the project. Management has to see the overall flow, develop a vision for the future, and lead its implementation. Management need to devote time to learn the value stream mapping to an extent that they can teach it. Changing the organizational focus from departmental thinking to value stream thinking is critical to success. Make sure your lean implementation team is on the shop floor, embracing hands-on approach and leading changes. Implement a set of team performance measures focused on reducing lead time, space, effort, deliveries, and missed deliveries. Post the maps where people will see them. Do not hide them. This way you can communicate what is going to happen. Six S is one of the most widely adopted techniques from the lean manufacturing toolbox. Along with standard work and total productive maintenance, 6S is considered a foundational lean concept as it establishes the operational stability required for making and sustaining continuous improvements. The primary objective of the tool is to create a clean, orderly environment, an environment where there is a place for everything and everything is in its place. Beyond this, any company begins their lean transformation with 6S because it exposes some of the most visible examples of waste. It also helps establish the framework and discipline required to successfully pursue other continuous improvement initiatives. 6S Workplace Organization is a process for creating and maintaining an organized, clean, and high-performance workplace, which serves as a foundation for continuous improvement activities. 6S needs to be performed in the correct order. You must give individuals responsibility for each task in their work areas within the office, warehouse, or factory. The first step, sort or clear out, focuses on removing any unnecessary items from the work area. This can include damaged goods, defective equipment, unneeded tools, or everything that stands still within the area and is not used. Items marked for disposal can be separated and put into a designated place, holding area, until a decision is made for their future. The second step, straighten or configure, focuses on effective and efficient placement of the items, tools which will be used. This might include labeling and putting frequently used items in accessible locations in order to reduce the amount of time to find and take them. The third step, shine or clean, comes after you have removed from the area unnecessary items and have put in order remaining tools. You should create a timetable and procedure for cleaning the area. Staff will take pride in a neat and tidy work area. They work much better, and from my experience, a clean warehouse, office or shop floor is more efficient. The fourth step, standardize or conform, is about creating standards or standard operating procedures for each work area. You should go through each process with the responsible employees and create, develop and display procedures and practices within the work areas. Procedures should be simple and easy to understand. A good practice should include more images and schemes than text in procedures, and put them on the walls so that people see and follow them. The fifth step, sustain or continually improve, ensures sustainability and continuous improvement of the success tool and procedures. Employees are encouraged to maintain and improve the implemented practices. Regular spot checks and audits should be conducted with rewards for high performance. The sixth step, safety, has been introduced recently by companies, which actually is at the heart of the process and an integral part of each one of the steps. Safety should be considered within the previous steps. Having it spelled out as an additional important step gives safety additional importance and focus. This focus can ensure that we do not otherwise overlook potentially hazardous situations, which may have escaped our initial look whilst in the grip of the excitement of implementing changes that have made our workplace more efficient and easier to operate. Remember that this methodology should be developed and applied to all areas within the company: administrative, offices, production, warehouses, and so on. The role of success in lean and quality. Success simplifies processes and reduces waste and non-value added activities while improving quality, efficiency, and safety. The tool is also effective in getting employees involved in the improvement process and owning their area of work, taking pride in how it looks and performs. Factories that have mastered the successes are growing factories. They experience results such as a reduction in waste pertaining to defects, movement, waiting, and transportation leads to fewer expenses and the time between the initiation and completion of processes. Less equipment malfunctions, which leads to equipment being used more efficiently. Fewer delays that allow a higher fill rate and prompt deliveries. Reduces flaws in work, which leads to lower costs due to less rework. Due to fewer flaws in the work, customers have a higher satisfaction rate and have fewer complaints. Better safety equates to fewer injuries at work and lower costs with absenteeism. Shift changes take less time and result in less downtime. Employee morale is boosted due to a cleaner work environment. These improvements will boost shareholder satisfaction rates and improve the company's profitability, salaries, and increase jobs. Let's now see some success applications. First application, zero waste, bringing lower costs and higher capacity. Wipe out standby waste in work in process inventory and finished products inventory. Cut down on standby waste due to conveyance equipment sluggishness, such as pallets, carts, forklifts. Reduce the waste that comes from using too much space and equipment. Eliminate motions that are inefficient during searching, sidestepping, and so on. Cut out steps that provide no value, such as picking up or putting down, counting, and carrying. The second application, zero injuries, bringing improved safety. When equipment is kept clean and running smoothly, you can spot mechanical failures as well as hazards almost immediately. Make sure that everything has a home in the workplace and be sure that aisles and rest areas are kept organized. Items should be in an area that will keep them and employees safe, such as an area that will prevent breakage. Emergency exits and equipment should be labeled in a manner that makes them easy to access in case of an emergency situation. The third application, zero breakdowns, bringing better maintenance. Maintaining equipment will lead to less waste buildup and dust, which can cause equipment breakdowns and high downtimes, as well as a short lifespan for equipment. Put plans in place to eliminate equipment waste and keep the workplace clean in order to make it effortless to see equipment failures. Maintain and check the equipment daily to eliminate breakdowns. Application number 4, zero defects, bringing higher quality. When the shop is messy, it's harder to spot imperfections. Be sure that everything has a place to go and put it in its place when you are finished with it. This lessens part and tool usage mistakes. Employees are more aware of how they are working and what they are making when the workplace is well maintained. Keep inspection tools and measuring equipment maintained properly and stored properly in order to ensure defects do not occur. Application number 5. Zero changeovers, bringing product diversification. The time spent searching for tools, dies and jigs can be eradicated via proper arrangement. Having equipment clean and neat boosts operational efficiency. Utilizing the 6 S's allows observers to comprehend the organization because it will be simplistic and transparent. Application number 6. Zero delays, bringing reliable deliveries. When defects are gone, deliveries go out on time. Employees and employers must have an excellent work environment in order to have a smooth operation. 6S's workshops report lower absenteeism rates. Operational efficiency is higher in waste-free workshops. Application number 7. Zero complaints, bringing greater confidence and trust. Goods that derive from a tidy workshop do not harbor defects. Products and goods that are made in a tidy environment cost less. Delivery times for goods that come from an efficient, tidy workshop are always prompt. And goods and products made in a tidy environment are safe. The last application, number 8, zero red ink, bringing corporate growth. People who work in 6S workplaces earn more respect and trust in their community. Customers feel better about their purchases when they know their goods or products are made at a manufacturing company that has eliminated accidents, waste, defects, and breakdowns. 6S benefits. 6S produces measurable benefits. One of the most reliable ways to track what is happening in the company, such as taking note of the amount of time it took to find an item in the workplace before the method was implemented, and then tracking the amount of time it took to find the same object when the 6S method was utilized. In the long run, a company can track the benefits of the 6S method by looking at the amount of accident reports. They'll find that accidents in the workplace are less and they don't have to spend as much time on training employees. Training employees in a workplace that is tidy, safe and organized is much easier and quicker. An excellent way to measure the benefits of 6S is to take photographs of the workplace before and after implementing the method. You can see how the method has brought order and a better appearance to the workplace. Concrete measurements are a complement to the pictures, fueling the momentum needed to sustain 6Ss. The target outcomes and benefits of a 6S program are: cut back on activities that do not add value to the company, scale down on supplier and employee mistakes, decrease the amount of time it takes to orient and train an employee, cut back on the amount of time it takes to find a tool, part or supply, scale back on the parts being stored unnecessarily in inventory and simultaneously cut back on inventory carrying costs, eliminate employee motion and movement of goods, enhance shop floor utilization, boost morale and safety of employees, boost product quality, and extend equipment life through more frequent cleaning and inspection. The fundamental concept of the theory of constraints is that every process has a single constraint and that total process throughput can only be improved when the constraint is improved. A very important result of this is that spending time optimizing non-constraints will not provide significant benefits. Only improvements to the constraint will accomplish the goal, achieving more profit. Thus, theory of constraints seeks to provide accurate and sustained focus on improving the current constraint until it no longer limits throughput, at which point the focus moves on to the next constraint. The underlying power of the theory of constraint flows from its ability to generate a tremendously strong focus towards a single goal, profit, and to removing the principal obstacle, the constraint, to achieving more of that goal. The 5 focusing steps. The theory of constraints provides a specific methodology for identifying and eliminating constraints referred to as the 5 focusing steps. As shown in the following diagram, it is a cyclical process. Identify the current constraint, the single part of the process that limits the rate at which the goal is achieved. Exploit, make rapid improvements to the throughput of the constraint using existing resources. Make the most of what you have. Subordinate, review all other activities in the process to ensure that they are aligned with and truly support the needs of the constraint. Elevate, if the constraint still exists, it has not moved, consider what further actions can be taken to eliminate it from being the constraint. Normally, actions are continued at this step until the constraint has been eliminated, until it has moved somewhere else. In some cases, capital investment may be required. Repeat. The 5 focusing steps are a continuous improvement cycle. Therefore, once a constraint is resolved, the next constraint should immediately be addressed. This step is a reminder to never become complacent, aggressively improve the current constraint, and then immediately move on to the next constraint. The thinking processes. The theory of constraints contains a sophisticated problem-solving methodology called the thinking processes. The thinking processes are optimized for complex systems with many interdependencies. They are designed as scientific cause and effect tools which strive to first identify the root causes of undesirable effects and then eliminate them without creating new ones. The thinking processes are used to answer the following 3 questions which are essential to the theory of constraint. What needs to be changed, what should it be changed to, and what actions will cause the change. Here are some examples of tools that have been formalized as a part of the thinking process include Current Reality Tree. Documents the current state. It's a diagram that shows the current state which is unsatisfactory and needs improvement. When building the diagram, undesirable effects, symptoms of the problem, are identified and traced back to their root causes, the underlying problems. Evaporating Cloud Tree evaluates potential improvements. It's a diagram that helps to identify specific changes that eliminate undesirable effects. It is particularly useful for resolving conflicts between different approaches to solving a problem. It is used as part of the process for progressing from the current reality tree to the future reality tree. Future reality tree documents the future state. It's a diagram that shows the future state, which reflects the results of implemented changes into the system that are designed to eliminate undesirable effects. Strategy and Tactics Tree provides an action plan for improvement. It's a diagram that shows an implementation plan for achieving the future state. It creates a logical structure that organizes knowledge and derives tactics from strategy. Drum buffer rope is a method of synchronizing production to the constraint while minimizing inventory and work in process. The drum is the constraint. The speed at which the constraint runs sets the beat for the process and determines total throughput. The buffer is the inventory level needed to maintain consistent production. It ensures that brief interruptions and fluctuations in non-constraints do not affect the constraint. Buffers represent time, the amount of time, usually measured in hours, that work in process should arrive in advance of being used to ensure steady operation of the protected resource. The more variation there is in the process, the larger the buffers need to be. An alternative to large buffer inventories is sprint capacity, or intentional overcapacity at non-constraints. Typically, there are two buffers. Constraint buffer, immediately before the constraint, protects the constraint, and customer buffer, at the very end of the process, protects the shipping schedule. The rope is a signal generated by the constraint indicating that some amount of inventory has been consumed. This in turn triggers an identically sized release of inventory into the process. The role of the rope is to maintain throughput without creating an accumulation of excess inventory. This suggests that the schedule should be built around the drum. Forward schedule on the drum and backward schedule on non-constraint. The nature of constraints. Constraints are anything that prevents the organization from making progress towards its goal. In manufacturing processes, constraints are often referred to as bottlenecks. Interestingly, constraints can take many forms other than equipment. There is a wide variety of opinions on how to best categorize constraints. A common approach is like this one. Physical, typically equipment, but can also be other tangible items such as material shortages, lack of people, or lack of space. Policy, required or recommended ways of working, may be informal. Examples include company procedures, union contracts, or government regulations. Paradigm, deeply ingrained beliefs or habits. For example, the belief that we must always keep our equipment running to lower the manufacturing cost per piece. A close relative of the policy constraint. Market occurs when production capacity exceeds sales. The external marketplace is constraining throughput. If there is an effective ongoing application of the theory of constraints, eventually the constraint is likely to move to the marketplace. There are also differing opinions on whether a system can have more than one constraint. The conventional wisdom is that most systems have one constraint, and occasionally a system may have 2 or 3 constraints. In manufacturing plants where a mix of products is produced, it is possible for each product to take a unique manufacturing path, and the constraint may move depending on the path taken. This environment can be modeled as multiple systems, one for each unique manufacturing path. The synchronous rules. A constraint is a resource with the highest load. A bottleneck is a resource that is unable to meet the current demand. A constraint critical resource is a resource that has the potential to become a bottleneck by, for example, periodic overload or sufficient unreliability. In plant scheduling, it is constraints which determine the throughput of the plant. For many, this is a whole new radical idea. There is generally only one constraint, like the weakest link in a supply chain. A balanced plant should not be concerned of management, but rather the continuing identification, exposure, and elimination of series of constraints. Eventually, outside constraints may be the determining factor. Examples are a market constraint or a paradigm constraint. While working on the alleviation of the constraint, the schedule should be organized around this constraint. Now let's examine the synchronous principles. First one, balance flow node capacity. For too long, the emphasis has been on trying to equate capacity of the work centers through which a product passes during production. This is futile because there will inevitably be faster and slower processes. Instead, effort should be made to achieve a continuous flow of materials. This means, for example, eliminating unnecessary queues of work in non-bottleneck work centers, and by splitting batches so that products can be moved ahead to the next workstation without waiting for the whole batch to complete. The utilization of a non-bottleneck is determined not by its own capacity, but by some other constraint in the system. A non-bottleneck should not be used all the time or overproduction will result, and therefore the capacity and utilization of non-bottleneck resources is mostly irrelevant. It is the bottleneck that should govern the flow. However, shorter runs, more changeovers are desirable on non-bottlenecks in order to smooth the flow to the bottleneck. Utilization and activation are not synonymous. This emphasizes the point that a non-bottleneck machine should not be activated all the time because overproduction will result. Activation is only effective if the machine is producing at a balanced rate, and this is called utilization. An hour lost at a bottleneck is an hour lost for the whole system. Since a bottleneck governs the amount of throughput in a factory, if the bottleneck stops, it is equivalent to stopping the entire factory. The implications of this for maintenance, scheduling, safety stocks, and selection of equipment are profound. An hour saved at a bottleneck is merely a mirage. In effect, it is worthless. This also has implications for many Lean and Six Sigma improvement activities. Bottlenecks govern both throughput and inventory in the system. A plant's output is the same as the bottleneck's output, and inventory should only be let into factory at a rate the bottleneck is capable of handling. The transfer batch may not and many times should not equal the process batch. A transfer batch is the amount of work in process inventory that is moved along between workstations. This quantity should not necessarily equal the production batch quantity that is made altogether. Instead, batch splitting should be adopted to maintain flow and minimize inventory costs. This applies particularly to products that have been already processed on bottleneck machines. They are then too valuable to have to wait for the whole batch to be completed. The process batch should be variable, not fixed. The optimal schedule should not be constrained by artificial requirements that a product must be made in one large batch. It will often be preferable to split batches into sub-batches. Lead times are the result of a schedule and cannot be predetermined. It's a disagreement with the use of standard pre-specified lead times, such as we usually find in MRP systems. Schedules should be assembled by looking at all constraints simultaneously. In scheduling, constraints may be machines, labor, and material. Look at them all together. In a typical factory, some products will be constrained by production capacity, others by market, and yet other by management inaction. At the heart of the theory of constraints is the realization that if a company had no constraints, it would make an infinite profit. Most companies have a very small number of true constraints. An excellent way to deepen your understanding of the theory of constraints is to walk through a simple implementation example. In this example, the 5 focus and steps are used to identify and eliminate an equipment constraint or bottleneck in the manufacturing process. Step 1. Identify the constraint. In this step, the manufacturing process is reviewed to identify the constraint. A simple but often effective technique is to literally walk through the manufacturing process looking for indications of the constraint. You should look for large piles of work in process on the plant floor. Inventory often accumulates immediately before the constraint. You should look for areas where process expeditors are frequently involved. You should review equipment performance data to determine which equipment has the longest average cycle time. Also, ask operators where they think equipment is not keeping up with the demand. The deliverable for this step is the identification of the single piece of equipment that is constraining process throughput. Step 2. Exploit the constraint. In this step, the objective is to make the most of what you have. Maximize throughput of the constraint using currently available resources. The line between exploiting the constraint, this step, and elevating the constraint, the fourth step, is not always clear. This step focuses on quick wins and rapid relief, leaving more complex and fundamental changes for later. For example, you can create a suitably sized inventory buffer immediately in front of the constraint to ensure that it can keep operating even if an upstream process stops. Check the quality immediately before the constraint, so only good parts are processed by the constraint. Ensure that the constraint is continuously scheduled for operation. Also, move routine maintenance activities outside of constrained production time and offload some constraint work to other machines or other companies. The deliverable for this step is improved utilization of the constraint, which in turn will result in improved throughput for the process. If the actions taken in this step break the constraint moves, jump ahead to step 5. Otherwise, continue to the next step 3, which is subordinate and synchronize to the constraint. In this step, the focus is on non-constraint equipment. The primary objective is to support the needs of the constraint. Efficiency of non-constraint equipment is a secondary concern as long as constraint operation is not adversely impacted. By definition, all non-constraint equipment has some degree of excess capacity. This excess capacity is a virtue as it enables smoother operation of the constraint. The manufacturing process is purposely unbalanced. Upstream equipment has excess capacity that ensures that the constraint buffer is continuously filled so that the constraint is never starved by the upstream process. Downstream equipment has excess capacity that ensures that material from the constraint is continually processed so the constraint is never blocked by the downstream process. Some useful techniques for these steps include implement drum buffer rope on the constraint as a way of synchronizing the manufacturing process to the needs of the constraint. Subordinate maintenance to the constraint by ensuring that the constraint is always the highest priority for maintenance calls. You may add sprint capacity to non-constraint equipment to ensure that interruptions to their operations can quickly be offset by faster operation and additional output. The deliverable for this step is fewer instances of constraint operation being stopped by upstream or downstream equipment, which in turn results in improved throughput for the process. If the actions taken in this step break the constraint, jump ahead to step 5. Otherwise, continue to the next step 4. Elevate performance of the constraint. In this step, more substantial changes are implemented to break the constraint. These changes may necessitate a significant investment of time and/or money, for example, adding equipment or hiring more staff. The key is to ensure that all such investments are evaluated for effectiveness. Here you can use performance data like overall equipment effectiveness metrics plus downtime analytics to identify the largest sources of lost productive time at the constraint. Target the largest sources of lost productive time, one by one. Implement ongoing plant floor reviews. Implement a setup reduction program to reduce the amount of productive time lost to changeovers. The deliverable from this step is a significant enough performance improvement to break the constraint. The last step 5 repeat the process. In this step, the objective is to ensure that the 5 focusing steps are not implemented as a one-off improvement project. Instead, they should be implemented as a continuous improvement process. If the constraint has been broken, the normal case, recognize that there is a new constraint. Finding and eliminating the new constraint is the new priority. If the constraint has not been broken, recognize that more work is required and a fresh look needs to be taken, including verifying that the constraint has been correctly identified. This step also includes a caution: be aware of inertia and complacency. Remain vigilant and ensure that improvement is ongoing and continuous.